Fusion on Earth. The Sun gains its energy from fusing protons to form helium nuclei. This requires the protons to be brought close enough together for the strong nuclear force to overcome the electrostatic repulsion of the positive charges. The Sun is 1/3 of a million times the mass of the Earth, and so the gravitational force produces immense pressures in the core. The core also has a temperature of around 16 million Kelvin. The Sun is huge, and so even unlikely events will occur often due to the massive numbers of protons available. We cannot hope to recreate these pressures or this number of protons on Earth, so what temperatures will we need to achieve fusion? As a fuel, we can use deuterium. This occurs naturally in water. We must get two deuterons or deuterium nuclei close enough for the strong nuclear force to overcome their electrostatic repulsion. This occurs at around 1.5 times 10 to the minus 15 meters, and at this distance the electrostatic potential, EP, will be given by the product of the two charges over 4 pi epsilon naught r, where epsilon naught is the permittivity of free space and r their distance of separation. Putting in the values, this gives a value of 1.53 times 10 to the minus 13 joules. To get this close, the deuterons must start with this amount of kinetic energy. Assuming they have half each, that is 7.7 times 10 to the minus 14 joules each. To find the temperature at which they would have this energy, we can use the kinetic energy of a particle given by 3 kT over 2, where K is the Boltzmann constant and T the temperature in Kelvin. So the temperature is 2 times the kinetic energy over 3K. Putting in the values, this gives a temperature of 3.7 times 10 to the 9 Kelvin. This is 230 times hotter than the core of the Sun. Clearly at these temperatures there is no material that can be used as a container. The container would melt and energy would be lost from the plasma, plasma being a state where nuclei and electrons are no longer attached to each other. The charged particles are contained within magnetic fields. They are contained in a shape called a torus, like a ring donut shape. The plasma spirals around the center of the torus. The plasma can be heated by passing a huge electric current through it, or by bombarding it with electromagnetic radiation, rather like in a microwave oven. Once fusion starts, the energy released should heat the plasma, leading to further fusions. Some of the energy released can be used to maintain the high temperature of the plasma, while some is removed by a coolant and then used to boil water, as in a conventional power station. At present, nuclear fusion is at the experimental stage, and more energy is put in heating the plasma than has been removed. If the many problems can be overcome, nuclear fusion uses a plentiful fuel of deuterium and produces no radioactive waste. Also, any problems would lead to a stopping of the reaction, so there is no chance of a runaway reaction taking place.